Okay, this is video 3. Alright, this one we're going to start talking about drivetrain geometry and turning. So one of the major attributes for a drivetrain's performance is how well it turns. And then there are two main properties which affect turning torque and turning scrub. So turning torque, remember that torque is a force that is perpendicular to a lever arm distance. So the turning torque, we can think about it as like how much force the wheels are putting on the ground, and then R would be like the distance between that force and the pivot point of your robot. That gives us the turning torque, and I'll show you some diagrams of that here. So the turning torque is the torque about the turning point, causes the robot to turn. Turning scrub is the friction which resists the robot turning. It's caused by the wheels dragging sideways on the ground. Turning scrub is also expressed as a torque, and in this case the torque would equal the friction that happens to be perpendicular to a lever arm distance. So this time the force is friction. So in a typical skid steer drivetrain, so the one where we think about all wheels being drive wheels, all of the wheels are exerting a force that contribute to the turning torque. However, they are also all dragging sideways, contributing to the turning scrub. So to help you visualize this, let's take a look at a picture. Now, this is a bad design. This is something that you would never build. So in this design, this bad design, we have 4 wheels, and they are all high direction wheels, or high traction wheels. We have 2 of them being powered. And then, so that's wheel 1 and wheel 2. Those are being powered. Wheel 3 and 4 are non-powered, and they are just sitting there. Our pivot point is right here in the center. So when we take a look at this, we can get an idea for how much torque, turning torque, this robot has. So this thing's trying to turn counterclockwise, so I have a force here, and I have a force here. And then the lever arm distance, which is the distance between where the force is applied and the pivot point, will be right here and right here. Let's call these X. And they're both the same value. So then the amount of torque that this robot is turning with would equal the force times X, because that force is perpendicular to that value X. So that's how much turning torque we have available. And I'm really looking at this because this is really just for one wheel, so the amount of total torque will be twice that, because we have 2 wheels that are being powered. Okay, so that's the turning torque. Now let's take a look at the turning scrub. So in this case, wheel 3, as this is trying to turn, there's this force of friction going against that. So as this is turning, those 2 wheels are being drug against the ground. And they have some perpendicular distance. I'll call this Y. So then the torque from the scrub would equal the friction times Y. And again, in this particular configuration, we have 2 wheels that are contributing to the scrub, so we would just double that. Again, you would never build this design. It's a dumb design, but hopefully this helps you to visualize what exactly turning torque and turning scrub are. So let's take a look at a better design. This one is a skid steer design. It's configured so that all 4 wheels are powered. So all four wheels are contributing to the turning torque, but they're also all contributing to the turning scrub. So looking at this, since these wheels are powered and we're trying to make a counterclockwise turn, all four of these wheels have a force that's trying to contribute it. And if we think about it, all of these wheels are the same distance, x, from our turning point. As these wheels turn, however, they are dragging against the ground. So we have this scrub, or this friction, between these wheels. We'd also have our distance y's between them. So if we knew all the numbers, we could go through and calculate all these. Now, turning torque and turning scrub are both torques about the robot's turning point. So something that was discussed, I believe, earlier, a torque is a turning force. And we got a linear force times a distance. And that force and distance must be perpendicular. So in these diagrams down below, they're just kind of blown up copies using x and y again. We can try to calculate the turning torque and the turning scrub for each individual wheel. We would then take that number and multiply it by 4 because there are 4 wheels. If I had 6 wheels, I would multiply that by 6. So the more wheels you have, the more turning torque you have, but also the more turning scrub you have. So, how can we reduce this turning scrub? Well, first off, we have to reduce the sideways friction. One way we can do that is by using omnidirectional wheels. Those are wheels that are designed to have 0 friction. Another way is to decrease the distance the wheel is from the turning point. So this one's a little harder to conceptualize. So let's scroll back up here and let's take a look at this. If I make y smaller, I would reduce the turning scrub acting on that wheel, because torque is equal to a force that's perpendicular to a lever arm distance. So in this case, the force is friction, and the lever arm distance in this case is y. So if I were to make y smaller, I would reduce how much turning torque, or I'm sorry, not turning torque, I would reduce how much turning scrub there is affecting on this robot. So that's what it means by reducing the distance between the wheel and the turning point. Now, a drivetrain with all omnidirectional wheels would have 0 turning scrub, so that's something to keep in mind. Now, something that might be interesting to note is that if I have a drivetrain with both high traction and omni wheels on it, the turning point is going to be directly between the 2 high traction wheels. So if I had something with high traction on the front, omnis on the back, the turning point would move upwards and position itself between the high traction wheels. This drivetrain would also have 0 scrub. But, the turning point, moving up there, the back end would swing about, and the front end would be like more fixed, which can be desirable. Now let's say that all we had were high traction wheels. Well, if I built a robot that was narrow and wide, what I would notice is that since this value is small, I would have low turning torque. And since this value for y is high, I would have high scrub. And that just comes from the fact that torque is equal to a force that's perpendicular to a lever arm distance. If I looked at a robot that was wide, but not very long, here I would get high turning torque and then low turning scrub. So that would be one way to design a robot that could handle this turning scrub. We would just simply have to make it wide and short. You wouldn't want to have it very long. Okay, so all of these examples discussed have been simplified to help illustrate their major underlying concepts. And another important consideration that may change the dynamics of these systems is the location of the turning point. In all these examples so far, the turning point has been at the exact center of the robot. Yeah, it's not always the case. The turning point often will vary based on the differences between the wheels, where you place the wheels, where you place your omnidirectional wheels, things like that. Now, friction also depends on the weight resting on the wheel. So if like the majority of your robot's weight is on the back end will have more friction than the front end, and that will affect the scrub as well. So where the weight is located can affect traction for the robot. Now, in order to make the robot turn better, you should primarily adjust three things: the chassis geometry, so wide versus narrow, long versus short, the difference in the coefficient of friction between the wheels, and then the location of the robot's center of gravity. So center of gravity is kind of like where all the weight is located. Okay, one more topic I want to cover real quick in this video. Gear train design. So the gear train is responsible for delivering the motor's power to the wheels. And we should have already discussed some different types of gearing and how to calculate the mechanical advantage of that. So first off, we can focus in on wheel speed. So we need to understand how to figure out how fast the robot moves across the field based on how fast the wheel is spinning. So each time the wheel spins, it makes one full rotation. It rolls forward a distance that is equal to the circumference. So if we calculate the circumference of the wheel, we know how far the robot travels for one wheel revolution. So circumference equals pi times the diameter of the wheel, or the way I like to think about it is 2 pi r, because twice the radius equals the diameter. So we can go through then. We know that if we're using 4-inch wheels, we know that the radius would be 2 inches. So the circumference would be 2 times pi times 2 inches. Pi, you can round pi to 3. So really we got 2 times 3, which is 6, times 2, which is 12 inches. So for our high traction and our omnidirectional wheels, which are 4-inch wheels, it'll travel about 12 inches for one rotation. So let's say that these wheels are traveling, so we got our 4-inch wheels on here, and let's say that they're spinning at 100 RPM, so revolutions per minute. What would be the robot's linear speed? So I've got 100 revolutions per minute, and what I could do is I need to understand that it also travels at 12 inches per revolution. So I could do a factor label. And I could say for 100 revolutions per minute, it's traveling at 12 inches per revolution. So really I'm left with 1,200 inches per minute. That seems awfully high. But remember, that's inches per minute. We can change that to inches per second, and if I did that, there are 60 seconds in a minute, so that'd be 1,200 divided by 60, or 120 divided by 6, so that's 20 inches per second. We could also try to find the mechanical advantage that would be needed to make the robot's wheel spin at 350. Mechanical advantage, we have our output speed equals our input speed divided by mechanical advantage. So mechanical advantage would equal the input speed divided by the output speed. So our input speed is 100 RPMs. We want our output speed to be 350 RPMs. So when we divide that up, we need to have a mechanical advantage of right around 0.28. All right, that's going to conclude our drivetrain design unit notes.